Hello, my name is Pranav, and this is my Physics 2212 Magnetic Braking Lab. The purpose of this lab was to demonstrate Faraday's law as it applies to a magnet falling down a tube of aluminum foil, and then to compare a computational model of this to the demonstration. We made a few assumptions. We assumed that the magnetic dipole moment was the same as from Lab 2, that there's no air resistance, and that things were measured correctly, and that the resistivity applies to the aluminum foil. The system was a magnet plus a tube, and the surroundings was everything else. There are three main concepts used. The first is Biot-Savart's law, which generates a magnetic field vector for a dipole at a given distance, magnetic flux, which is the amount of magnetic field that is passing through a certain area, and Faraday's law, which relates the change of magnetic flux of an area to a generated voltage. The results were that as the bar fell, it was slowed down compared to when it was dropped outside the tube. The experimental average for the fall was 1.51 seconds, and the computational time was 1.677 seconds. This is a relatively large difference. Procedure for this experiment was relatively simple. First, we used a magnetometer to find the north pole of the magnet, which was then marked. We found a tube of aluminum foil, and the dimensions were measured. A phone was set up to record, and the magnet was dropped 5 times. The recording was used to judge the amount of time it took to come out the tube. A computational model was then created using GlowScript, and this model was then compared to the experimental results. So here's a quick summary of the experimental data. You can see the time it took on each trial and the average, and also the measured dimensions. The tube was 1 foot across, and had a 1 centimeter width of aluminum and 2 centimeters of inner radius. The magnet's mass was 0.023 kilograms. So this is an overview for the computation for this lab. In this first section, we're setting some initial variables and measured constants such as the length, width, and radius. And in the second section, where it says dipole B, we're defining the magnetic field strength at a given distance using the formula from Biot-Savart's law. And then we will then calculate the d flux dt, so the change in flux over time. So the way we did this is that we multiplied the dipole B times the area, and then took the derivative of this with respect to time. And so then we return a value for df dt. We also created a value for the gravity vector, which is just -1 mg. And we then found the magnetic force at the ring. So to do this, we use this little code section here. The net force was then found by adding up the magnetic force and the F gravity. And then we updated the bar's velocity and position. So this generated the curve as seen here in this image, which is the magnet as it's fallen to the bottom of the tube. Note that the color of the current here is blue. So what you can see is that the magnitude of the velocity increases up to a point until the magnetic force starts to increase much more faster, and it starts to level off. And here, the F net is 0 as the velocity is constant. It then falls back down as it starts to leave the tube. So now we're going to get into some questions and conclusions for the lab. So the first question asks, since red and blue indicate current in different directions, which color corresponds to which direction as viewed from above? So in my case, B was upwards and increasing because the magnet was north up. That means that dB dt was upwards. In order to counteract this, the current will then create a downwards dB dt, which would be done through a clockwise rotation as per the right-hand rule. And since my simulation was blue, that means that blue is clockwise and red is counterclockwise. If we were to flip the magnet so that north was pointing down, physically nothing would change as the induced EMF would still cause a resistance to the motion of the magnet. However, the current would flip, so now B would be pointing downwards and increasing, meaning that dB dt is downwards. In order to resist this, the current would have to create an upwards dB dt, meaning that it would rotate counterclockwise. The motion would not change though. So when we're comparing the total in-time tube of the real world to the computational system, there was a decent discrepancy of about 0.26 seconds, which is pretty high, and this is likely due to the computational model not taking into account air resistance, and also not remeasuring the magnetic dipole moment. I think that if we had remeasured it, it would have been more accurate. And so, as we discussed earlier, looking at the velocity versus time plot, there's a constant velocity at a lot of the points of the graph, meaning that the net forces are equal, so the gravity force and the magnetic force are equal for a decent amount of time. So now we're getting into the what if questions. So what if the resistivity of the conductor was reduced as close as possible to 0? How would this change the dynamics? Given the reduced resistivity, this would mean a reduced resistance overall. And since V equals IR, current and resistance are inversely proportional, an increased current would mean a greater resisting force, which would lead to the magnet falling slower, having a smaller terminal velocity magnitude, and taking more time to exit. And so what if some holes or slots were cut into the tube? How would this affect the currents in the model? If holes or slots were cut in, you wouldn't have a complete loop for current to travel in, and so you would not be able to actually have a current. And so this would mean that the sections of the tube would no longer have a current to generate an EMF, and this means that the overall current would decrease and the overall magnetic force would decrease. This will cause the magnet to fall faster. Overall, the lab was successful and the computational model was able to be derived and compared to the experimental model.